Imagine holding the blueprint not just for a galaxy, but for an entire universe. What if the boundaries of reality are just lines in a vast, complex code? We've long debated whether consciousness can exist within simulated worlds. Yet what if our very existence is part of the grandest simulation of all? As technology approaches the power to recreate reality itself, the line between what's real and what's simulated begins to blur. And suddenly, the question isn't just whether we could simulate a universe, but whether we already are in one. Stay with me as we explore the fascinating possibilities, blending philosophy and computation, and ask, could our universe be nothing more than a highly advanced simulation? The concept of universe simulation. The idea of simulating an entire universe often rests on the premise that consciousness and physical reality can, in principle, be reducible to computational processes. Proponents of this view argue that if the universe functions according to consistent physical laws, such as quantum mechanics, general relativity, and thermodynamics, that it might be possible to mimic these laws entirely within a sufficiently advanced computational system. From a philosophical perspective, this raises profound questions about the nature of reality itself. Are we living inside some kind of cosmic computer? If so, the universe's fabric could be viewed as a vast data structure, with particles, fields, and even space-time emerging from the code running beneath. In practical terms, the challenge lies in the staggering complexity involved. Simulating even a tiny corner of the universe at quantum resolution requires processing power and data storage capabilities that are currently unimaginable. However, assuming exponential growth in computational technology, some theorists speculate that a future civilization might develop hyper-advanced quantum computers or other exotic hardware capable of running such detailed simulations. The essence of the concept is often linked to the idea of a mother universe, a computational substrate capable of rendering countless nested simulation layers, one universe within another like digital Russian dolls. The question then becomes not just whether we could technically simulate a universe, but whether we possess the philosophical understanding to justify doing so. Simulation theorists often invoke ideas from classical logic and information theory, suggesting that reality might itself be fundamentally informational. The universe, by this logic, could be akin to a grand algorithm, evolving according to predetermined rules that can be encoded and executed within a computational framework. The notion also ties into the famous ancestor simulations hypothesis, which suggests that sufficiently advanced civilizations might run detailed simulations of their ancestors to understand history better. If true, the idea of our universe being a simulation isn't just sci-fi. It becomes a plausible hypothesis grounded in future technological potential and the nature of information. Yet, the pursuit of simulating an entire universe raises philosophical dilemmas about authenticity and consciousness. Would the beings within such a simulation experience true awareness or merely mimic consciousness convincingly? The question challenges the boundary between what is real and what is artificially generated. If consciousness is a product of physical processes, then a perfect enough simulation might also be conscious, blurring the lines between simulation and reality. Ultimately, the concept of universe simulation invites a deep reconsideration of the essence of existence, prompting us to revisit our assumptions about reality's ultimate nature, whether it's a grand computational horizon shrouded in mystery or something inherently different. Historical perspectives on simulating reality. Throughout human history, the quest to understand and replicate reality has been a profound philosophical pursuit. Ancient civilizations often pondered the nature of existence, mythologies and religious doctrines depicting worlds shaped by divine forces. Philosophers like Plato imagined a realm of perfect forms, hinting at the possibility that our tangible universe might be a shadow of a higher, more real reality. As scientific thought evolved, the idea of simulating reality took on a new dimension, moving from metaphysical speculation toward tangible experimentation with mechanical and mathematical models. Early thinkers posited that if reality operated according to consistent laws, then perhaps it could be reproduced through intricate calculations or mechanical devices. With the advent of classical computation and digital simulation, the idea of recreating worlds gained a more concrete footing. The development of computers enabled the simulation of physical systems, planets, weather patterns, atomic interactions, each pushing closer to the notion that entire universes might one day be simulated. Philosophers such as Leibniz and Descartes contemplated the notion that our own universe could be akin to a vast, divine computation. In the modern era, scientists like Konrad Zuse and John von Neumann envisioned early digital universes, concepts not merely confined to science fiction, but presented as feasible scientific hypotheses. These ideas laid groundwork for contemporary debates about whether the universe itself is a form of computation, a long-standing hypothesis that aligns with the simulation argument put forth by Nick Bostrom. Historically, thought experiments have consistently challenged the limits of simulation. The idea that an advanced civilization could simulate conscious beings raises profound questions about reality and authenticity. If such simulations are possible, then hypothetical ancestors, us, might ourselves be part of a grand computational construct. This concept aligns with philosophical arguments that treat consciousness as an emergent property of complex information processing, suggesting that if the substrate changes, say, from biological to silicon-based, the experience of reality could remain intact. The boundary between material reality and simulated existence blurs as computational power increases. Over time, what once was pure philosophy now intersects with the practical ambitions of technological pioneers, hinting that simulating entire universes might be an eventual, if distant, reality, spurring discussions on ethics, consciousness, and the fabric of existence itself. Foundations of computational universes. The notion of simulating an entire universe hinges on the premise that reality itself can be understood through information processing. At its core, the foundation of computational universes is rooted in the idea that the fabric of existence may be composed of underlying data structures and algorithms. This perspective aligns with the digital physics hypothesis, which suggests that the universe operates akin to a gigantic computation. If the universe is indeed discrete at a fundamental level, say, like a cellular automaton, it becomes theoretically possible to model it using sufficiently advanced algorithms and hardware. This brings us to the question: as computing power advances, could we, in principle, replicate every particle, force, and quantum state within a simulated cosmos? The concept is fascinating, but not without profound challenges. One of the most significant hurdles relates to the sheer scale and complexity involved. Our universe contains an estimated 10^80 particles, and capturing every quantum interaction requires an astronomical amount of processing power. While quantum computing promises exponential improvements over classical computers by manipulating qubits instead of bits, it still faces fundamental limits rooted in thermodynamics and information theory. Some theorists argue that, even with infinite resources, simulating the universe with perfect fidelity might remain impossible due to the inherent unpredictability implanted by quantum indeterminacy. The Heisenberg uncertainty principle, after all, implies a certain level of irreducible randomness, potentially meaning any simulation would only approximate real phenomena, rather than reproduce them exactly. Philosophically, the foundations of computational universes challenge traditional notions of reality. If a universe is programmable, it blurs the lines between the real and the simulated. This dovetails with simulation theory, which proposes that what we perceive as reality could itself be a vast, ever-running program. Some theorists propose that what we interpret as consciousness might emerge from complex information processing, potentially within any sufficiently detailed simulation. In this light, the question becomes: if a universe is built upon the rules of computation, is there any meaningful distinction between a natural universe and one generated by an algorithm? This line of thought opens imaginative possibilities about the nature of existence itself, suggesting that reality might be akin to a nested hierarchy of simulations, each possibly generated within a larger computational framework. Considering the physical laws that govern our universe, their mathematical elegance hints an underlying code or algorithmic structure. The first law of thermodynamics and Einstein's equations of general relativity are expressed through concise mathematical formulas that could be interpreted as code snippets of a cosmic program. If these laws are, in essence, the syntax and semantics of a computational language, then simulating a universe might involve decoding or rewriting this program at an ultimate level. The challenge lies in understanding whether the universe's complexity arises from simple rules, like Stephen Wolfram's hypothesis about cellular automata, or whether it emerges from inherently unpredictable quantum processes. This touches on whether a computational universe would be deterministic, rendering all events traceable and predictable, or inherently probabilistic, leading to an ongoing debate about free will, randomness, and the limits of simulation accuracy. Ultimately, the foundations of computational universes intersect deeply with both technological and philosophical inquiries. While current technology is far from capable of simulating even a fraction of a universe's detail, theoretical frameworks continue to evolve. They compel us to reconsider what constitutes reality and whether consciousness or self-awareness could also be simulated by purely computational means. Whether or not we can ever reconstruct a universe in silicon or quantum bits remains an open question, one that blurs the boundaries of science, philosophy, and metaphysics. The notion of a universe built from code serves as a mirror reflecting human curiosity about origins, meaning, and the ultimate nature of existence itself. Theoretical limits of simulation complexity. The concept of simulating a whole universe hinges on the assumption that the universe itself is, at some fundamental level, information and computationally representable. According to digital physics, the universe might follow rules similar to those of a giant cellular automaton, which raises profound questions about the amount of information needed to depict reality accurately. As the complexity of such a simulation increases, so does the demand for processing power and memory, exponentially so in some cases. The laws of physics, despite their elegant simplicity at the core, generate a staggering amount of data when scaled to the cosmic level. To simulate every particle, gravitational interaction, electromagnetic force, and quantum event in detail would require an unimaginable amount of computational resources that may be forever beyond reach, given the constraints of our universe's physical laws and the limits of computation. The limits of what can be simulated are also tied to the notion of computational entropy and the principle of finiteness embedded in our universe. Every universe, as per current scientific understanding, appears to have finite energy and information capacity, despite its vast size and complexity. This means an ultimate boundary exists. Beyond a certain level of simulation detail, the system becomes either incomprehensibly large or computationally impossible to sustain. Take, for example, the concept of quantum complexity. Quantum states can entangle vast numbers of particles, and accurately simulating such states would require exponential resources relative to the number of particles involved. So, realistically, there's a threshold beyond which simulating a universe, down to every quantum detail, becomes an insurmountable task. Furthermore, the physical substrate of the simulation, if it exists, sets its own limits. Whether run on classical supercomputers, quantum computers, or some hypothetical new technology, the hardware imposes boundary conditions that can't be bypassed. A classical computer, bound by the laws of classical physics, cannot efficiently simulate quantum phenomena without exponential overhead. Meanwhile, a quantum computer might reduce some of these overheads, but still faces issues like decoherence, error correction, and scalability. Even if hardware were unlimited, causality and the speed of information transfer place ultimate speed limits. For a universe-sized simulation, the latency involved in updating every part of the system could prohibit real-time or even feasible simulation. Ultimately, many thinkers question whether the universe's intrinsic physical and informational constraints form a hard ceiling on simulation complexity. Could some deeper physical principle, perhaps holography, the finite nature of information, or intrinsic computational bounds like those proposed by theoretical computer science, foreclose the possibility entirely? Or do they instead suggest a hierarchy of simulation layers, with each layer effectively rich enough to mimic the previous one? The debate intertwines physics, computer science, and philosophy, probing whether ultimate simulation is a question of technology's limits or if the universe itself reflects a form of computational finiteness that cannot be bypassed. In the end, whether we could ever faithfully simulate a whole universe may hinge less on theoretical limits and more on the metaphysical nature of reality itself, an inquiry that continually blurs the line between what is physically possible and what is fundamentally beyond reach. Physical laws as computational rules. The concept that the universe operates on a set of computational rules stems from the idea that all physical phenomena can be distilled into fundamental algorithms, mathematical laws governing particles, forces, and space-time itself. This perspective aligns with the digital physics hypothesis, which suggests that the universe is inherently computational at its core. Instead of viewing physical laws as mysterious, ineffable rules handed down from some divine source, they can be seen as precise algorithms that dictate how the universe evolves. Quantum mechanics, for example, describes particles not as static objects but as wave functions governed by the Schrödinger equation, an intricate mathematical rule that determines probabilities and interference patterns, much like lines of code predict outcomes in a computer simulation. To simulate a universe computationally, one must translate these laws into forms compatible with digital or analog computing frameworks. This involves discretizing continuous variables such as space and time, transforming the smooth fabric of space-time into a lattice or grid, where each cell acts like a pixel in a vast cosmic image. Cellular automata, simple programs that evolve deterministic rules over discrete grid points, have demonstrated how surprisingly rich complexity can emerge from straightforward algorithms. In theory, a sufficiently detailed cellular automaton could replicate the behavior of entire universes, with rules that reproduce gravitational interactions, electromagnetic fields, and even the emergence of life. Whether this is feasible depends on whether the universe is truly discrete or continuous at its fundamental level. The challenge, of course, is scale. Physical laws operate across an enormous range of magnitudes, from subatomic particles to cosmic structures. Trying to simulate every detail at all scales would require an unimaginable amount of computational power, something like running a universe-sized program on an unimaginably advanced machine. Yet, if the universe's laws are truly algorithmic and finite in complexity, then perhaps only a relatively small set of essential rules underpins the entire cosmos. This idea raises philosophical questions. Could the universe be a sort of grand, cosmic executable program, run on some ultimate computer? If so, the line between simulation and reality blurs, posing the possibility that our own universe might itself be a sophisticated computation, a hypothesis that tantalizes scientists and philosophers alike. Ultimately, asking whether physical laws can serve as computational rules ties into the broader question of whether reality itself is a form of information processing. Such a viewpoint invites us to think of existence not just as matter and energy, but as the unfolding of a vast, intricate code, an ongoing computation. If this is true, then a universe's complexity emerges from the recursive play of simple rules, much like the Mandelbrot set or cellular automata. It suggests that understanding the universe's code might unlock the secrets of its origin, consciousness, and ultimate fate, if such concepts even have meaning within a framework where rules are computational rather than mystical. This intersection of physics, mathematics, and philosophy continues to challenge and expand our conception of what reality might truly be. Quantum mechanics and simulation feasibility. Quantum mechanics, with its inherently probabilistic nature and non-intuitive principles, presents a formidable challenge when contemplating the simulation of a universe at its most fundamental level. Unlike classical physics, where objects follow predictable trajectories governed by Newtonian laws, quantum entities exist as wave functions that encode probabilities rather than certainties. In principle, simulating such a system would require accounting for a vast, potentially infinite, number of quantum states. When considering the entire universe, this complexity becomes staggering. Every particle, field, and quantum fluctuation contributes to a computational load that exceeds any conceivable capacity. Yet, in recent decades, advancements in quantum computing have begun to hint at the possibility of more efficient simulation techniques. Unlike classical computers, quantum machines exploit superposition and entanglement, potentially allowing them to handle the exponential state spaces intrinsic to quantum systems more gracefully. Nevertheless, the feasibility of simulating the universe's quantum fabric hinges on understanding and manipulating quantum decoherence and entanglement. Decoherence, the process by which quantum systems lose their coherence and behave classically, creates a boundary between accessible quantum states and emergent classical realities. To simulate the universe, a machine would need to maintain coherence across an unfathomably large number of particles and fields, something that pushes the limits of current quantum error correction and hardware stability. Even the most advanced prototypes today can only simulate small quantum systems for brief periods. Scaling this up to the universe's level, with roughly 10^80 particles, according to estimates, remains a theoretical leap as enormous as the universe itself. On a philosophical plane, the question becomes whether such a simulation is fundamentally possible or if quantum mechanics secretly imposes an insurmountable barrier. The universe's quantum nature implies that any simulation must inherently deal with probabilities, uncertainties, and non-local interactions. This raises intriguing questions about whether a simulated universe would need to replicate not just the observable phenomena, but also the underlying wave function that encodes every possible state. If a hypothetical super-advanced civilization or an AI could harness quantum algorithms beyond our current understanding, they might circumvent some limitations. Still, the sheer computational resource demands could translate into a Moore's law-sized explosion in complexity, effectively demanding an almost divine level of processing power. Real-world efforts in quantum simulation research shed light on the current boundaries and future potential of such endeavors. For example, simulating lattice quantum chromodynamics, QCD, a theory describing the strong force within atomic nuclei, has already pushed quantum hardware to its limits. Such focus simulations reveal that the universe's quantum nuance is not just central to its structure, it is also a barrier. To faithfully recreate the entire cosmos' quantum behavior, one would need not only unprecedented computational resources, but also a profound understanding of quantum gravity, a frontier yet uncharted. The idea that the universe itself might be a giant quantum informational system, akin to a gigantic quantum computer, becomes a tantalizing thought experiment. If true, this shifts the question from can we simulate to are we perhaps already living inside a quantum simulation of sorts. The role of consciousness in simulated universes. Consciousness remains one of the most perplexing phenomena in both philosophy and science, yet assumes a pivotal role when contemplating the simulation of entire universes. In the realm of simulation theory, consciousness isn't merely an emergent property, but could be the very cornerstone that defines whether a simulated universe possesses genuine experiential reality. If we accept that consciousness is fundamentally linked to information processing or some form of intrinsic awareness, then the question arises, can a sufficiently advanced computational system produce not just complex patterns, but authentic subjective experience? This idea breathes life into the hypothesis that a simulated universe, if designed with the right architecture, might contain conscious entities that are indistinguishable from their real counterparts. One compelling argument involves the idea that consciousness could be a universal computational phenomenon, or at least reducible to computational processes. If consciousness emerges from particular configurations of information processing, then a detailed enough simulation might harbor conscious beings without any need for physical substrate beyond the simulation's code. For example, some neuroscientists speculate that if they could replicate the precise neural dynamics of a human brain within a computer, the simulated brain might produce subjective experience. Extending this logic, entire cosmoses, with their vast complexity and intricate feedback loops, could support conscious entities simply by virtue of their informational structure. From this perspective, consciousness isn't tied to carbon or biological tissues, but to the abstractions that underpin physical law itself. The question, however, becomes thornier when considering whether simulated consciousness is genuine or merely an illusion. Is a simulated mind truly conscious, or does it merely mimic conscious behavior? Some philosophers argue that if the internal subjective experience is absent, if there's no real feeling behind the responses, then it's just a simulation of consciousness, not consciousness itself. Conversely, others maintain that if the simulation's internal processes are indistinguishable from those of biological consciousness, then to all practical purposes, it is conscious. This debate touches on the infamous hard problem of consciousness, understanding why and how subjective experience arises from physical processes. If consciousness depends on the substrate, then a simulation might be limited, but if it hinges solely on informational patterns, then the entire universe could potentially be simulated with conscious entities. Ultimately, exploring the role of consciousness in universe-scale simulations pushes the boundaries of both scientific understanding and philosophical inquiry. It challenges us to reconsider what it means for something to be real or authentic. Whether a universe can be truly simulated hinges on whether consciousness can be generated purely computationally or whether it demands something beyond physical or informational structure, something perhaps metaphysical or yet to be understood. As technology advances and our grasp of consciousness deepens, these questions will increasingly shape the future of simulation research and our understanding of reality itself. Technological advances needed for cosmological simulation. The leap from simulating local phenomena, like weather patterns or molecular interactions, to recreating an entire universe demands an exponential increase in computational power and sophistication. Today's supercomputers, with their hundreds of thousands of cores and petabytes of memory, can model galaxy formation, nuclear fusion, and even the large-scale structure of cosmic filaments. Yet they fall vastly short of capturing the full complexity of a universe at its most comprehensive level. To bridge this gap, hardware must evolve beyond current quantum and classical limits, accommodating unprecedented levels of parallelism, data throughput, and energy efficiency. Simulating a universe requires not only raw processing power, but also paradigm-shifting advances in algorithms and data structures. Current cosmological simulations often rely on approximations, smooth particle hydrodynamics, or grid-based methods that balance accuracy with computational feasibility. Achieving a truly holistic simulation would demand algorithms capable of capturing quantum effects, dark matter interactions, gravitational waves, and even the emergent phenomena arising from countless microstates. These algorithms must be adaptable and scalable, capable of integrating diverse physical models seamlessly to reflect the universe's interconnected fabric. Machine learning and artificial intelligence stand as promising tools in this domain, helping optimize resource allocation and predict complex interactions, yet their deployment at such a scale is still in embryonic stages. On a more philosophical level, the challenge hinges on the nature of information and the limits of simulation fidelity. To faithfully recreate a universe, the necessary data architecture must encompass every detail, every particle trajectory, electromagnetic fluctuation, quantum state, at scales that could be astronomically large. The storage and retrieval systems needed would far surpass today's capabilities, potentially involving the development of new forms of quantum memory or holographic data frameworks. If we imagine a universe being itself a computational process and consider simulation theory, mankind's pursuit becomes a quest not just for technological supremacy, but for understanding whether we are already living within an intricately simulated cosmos. These questions open debates about whether simulating a universe is a matter of sheer capability or whether there are fundamental constraints rooted in the fabric of reality itself. Ultimately, the task is not solely about engineering prowess, but also about reconciling the philosophical implications of such an achievement. Whether it's possible or not, the pursuit pushes the boundaries of what it means to understand existence. That to simulate a universe is to grapple with its deepest laws, symmetries, and potentialities. If technological progress continues on its current trajectory, some argue it might someday be feasible, but only by transcending decades, if not centuries, of incremental innovation, an endeavor that compels us to rethink computation, matter, and the very definition of infinity itself. Ethical and moral implications of universe simulation. Some argue that if we possess the technological capacity to simulate entire universes, recreating not just matter and energy, but consciousness itself, then the ethical landscape becomes a labyrinth rooted in questions of rights, responsibilities, and the very nature of existence. If a simulated universe hosts sentient beings capable of experiencing pain, joy, fear, or hope, do the creators bear moral obligations toward those inhabitants? The scenario echoes debates about artificial intelligence and the morality of creating sentient machines. Stripping this down to a cosmic scale forces us to confront a magnitude of ethical responsibility that is both mind-boggling and deeply unsettling. The act of simulating a universe raises concerns about consent and autonomy. Unlike a controlled laboratory experiment on non-sentient matter, a universe with conscious entities might have beings unaware of their simulated nature, potentially suffering trauma or existential crises if their creators manipulate their reality or discontinue the simulation. This echoes philosophical thought experiments like the brain in a vat or the experience machine, but amplified to cosmic proportions. Is it morally justifiable to create worlds where suffering can be induced merely for exploration, entertainment, or scientific curiosity? The moral calculus becomes more complicated when considering that such simulations could involve billions or even trillions of sentient beings, raising questions of whether their rights should mirror ours and how to prevent exploitation within these digital realms. Further compounding these issues are the broader implications for the creators themselves. If humans develop the capability to simulate universes, does that grant us divine-like authority? This power carries with it the risk of playing God, which has historically been fraught with hubris and unintended consequences. In this context, questions about humility and moral restraint emerge. Would wielding such power obligate us to establish ethical frameworks that prevent harm or misuse? Or would the potential for infinite experimentation justify a reckless approach, disregarding the suffering or autonomy of simulated entities? These questions mirror ongoing debates in bioethics and AI governance, but on a scale that transcends current human experience. On a more philosophical note, the moral implications involve the very nature of reality and consciousness. If our universe is nothing more than a simulation, then our moral frameworks, predicated on notions of intrinsic value, autonomy, and suffering, may require reevaluation. Are simulated beings truly deserving of moral consideration if their consciousness is programmed? Does the divine or creator role in universe simulation impose a moral duty akin to that of traditional gods, or does it redefine our moral responsibilities entirely? Such considerations challenge the boundaries of ethics, combining the pragmatic with the metaphysical in an ongoing dialogue about the meaning and morality of creating worlds, real or simulated. Philosophical questions of reality and illusion. The notion of simulating a whole universe stretches the limits of both technological possibility and philosophical inquiry. Current computational power, although rapidly advancing, still falls far short of recreating a universe with the complexity and scale of our own. Yet, some thinkers argue that as simulation technology progresses, particularly through breakthroughs in quantum computing and artificial intelligence, creating entire virtual universes could become plausible. These hypothetical constructs would encompass not just the fabric of space-time, but also the multitude of quantum states, particles, and forces that define physical reality. But beyond the technical feasibility, questions about what constitutes reality become increasingly tangled when considering simulation. If a universe were simulated with such fidelity that its inhabitants could not distinguish it from real existence, what philosophical questions arise about the nature of being? The simulation hypothesis, famously championed by philosopher Nick Bostrom, suggests that we might be living in an artificial realm created by a more advanced civilization. This concept raises profound doubts about the authenticity of our perceptions. How can we be sure that our consciousness isn't just a complex pattern within a vast computational matrix? When reality is reducible to information processing, the boundary between illusion and genuine existence becomes disturbingly blurry. Simultaneously, the idea that our universe might itself be a simulation invites a reconsideration of classical philosophical traditions about reality. Plato's allegory of the cave illustrates how our senses can deceive us, suggesting that what we perceive is a shadow of a deeper truth. In the context of simulation theory, our perceived universe could be analogous to the shadows on the cave wall, projections within a more profound layer of reality that remains inaccessible. The possibility that everything we experience could be an illusion challenges the very foundation of epistemology, how we know what we know. Could consciousness itself be a programmed illusion? If so, then notions of free will, morality, and purpose might all be redefined within this computational framework. Some argue that simulating a universe isn't just a technical question, but a philosophical one about the nature of consciousness. If consciousness emerges from complex information processing, whether in biological brains or digital simulations, then creating a simulated universe with conscious beings becomes conceivable. Yet, the problem of subjective experience, or qualia, persists as a thorn in the side of these theories. Would simulated beings possess genuine consciousness, or are they merely complex automata that mimic conscious behavior? If consciousness depends on a specific biological substrate, then a simulated universe might be fundamentally incapable of hosting true sentience, raising further doubts about the idea that a simulated universe could mirror or even contain consciousness identical to our own. These questions create layers of philosophical debate that intertwine reality, illusion, existence, and the limits of human understanding. The multiverse hypothesis and simulated realities. The idea that our universe might be a simulation has gained significant traction in both philosophical discussions and scientific circles, especially when considering the multiverse hypothesis. The multiverse posits that our universe is just one of countless others, each with its own set of physical laws, constants, and initial conditions. This concept challenges traditional notions of a singular, unique universe and opens up the possibility that reality as we know it is but a small fragment within an immense, perhaps infinite, ensemble of universes. From a computational standpoint, this raises the provocative question: could a simulation encompass not just a single universe, but the entirety of multiversal realities? If we think about advanced civilizations developing hyper-advanced computational capacities, then simulating a multiverse might not be beyond the realm of future technology, assuming they could overcome staggering computational demands. Taking the multiverse into account blurs the lines between physical reality and simulated constructs. If we accept the premise that our universe is discrete enough in its fundamental particles and constants, like the Planck length or the fine structure constant, it suggests that a sufficiently powerful computer might simulate not just one universe, but thousands or millions of alternate realities, each governed by different emergent rules. The implications stretch beyond mere entertainment. They challenge our understanding of consciousness, free will, and the nature of existence. Suppose infinite or vast numbers of simulations already exist, layered within each other, each with its own sentient beings unaware of their simulated status. This recursive idea is reminiscent of philosophical puzzles like the brain in a vat or the simulation hypothesis popularized by thinkers like Nick Bostrom, who argued that if future civilizations could efficiently simulate universes, the probability that we are living in a base reality diminishes significantly. Then, consider the computational requirements involved. To simulate a universe with comparable complexity to our own, housing billions of galaxies, trillions of stars, and intelligent life, would demand a level of processing power that seems astronomically high. Quantum computing offers some theoretical promise here, with its potential to process vast states simultaneously, but whether such resources could be used to simulate entire multiverses remains speculative. Yet, the philosophical beauty of this idea is that it raises a fundamental question about reality itself. If a sufficiently advanced simulation could produce conscious entities indistinguishable from real beings, what distinguishes reality from simulation? Is it merely a matter of complexity and scale? Or does consciousness itself become the dividing line? This line of thought urges us to reconsider not only the nature of our universe, but the nature of existence itself. Such contemplations serve as a nexus where physics, metaphysics, and computer science intersect. The idea of simulating multiverses underscores both the power and the limitations of human understanding and technological progress. If our universe is a simulation, then the multiverse hypothesis becomes a crucial piece of a much larger puzzle, one that invites us into a realm where the boundaries of reality are fluid and where the act of creation itself could be a fundamental aspect of existence. Whether or not such simulations are feasible, pondering the possibility sharpens our sense of curiosity about what is ultimately real and how much of our universe might be the result of clever code rather than cosmic coincidence. Potential evidence for existing simulations. Quantum mechanics and computational theory intertwine in ways that suggest the universe might be a vast, intricate simulation. One of the most compelling lines of thought revolves around the limits of our own understanding of physics. For instance, the discovery of phenomena like quantum entanglement, where particles seem instantaneously correlated regardless of distance, raises questions about the fundamental fabric of reality. If our universe is a simulation, these quirks could be artifacts of how the simulation's code is designed or remnants of the underlying architecture that hosts it. The idea is that a simulated universe might operate with constraints similar to those of a computer program, where information transfer is maximized efficiently, leading to seemingly weird effects that are difficult to reconcile with classical physics. Further evidence can be observed in the mathematical structures underlying physical laws. The universe appears to abide by elegant, precise mathematical formulas, like Einstein's field equations or the Schrödinger equation, that suggest a coded reality. The astonishing accuracy with which these equations predict phenomena hints at an underlying computational logic. Some theorists argue that the universe's mathematical nature resembles a sophisticated simulation encoded in code. The notion that type systems and error-correcting codes in computer science bear resemblance to physical constants and symmetries isn't coincidental. It might indicate that our cosmos is a product of complex programming, meticulously tested and refined, much like software crafted by developers with a purpose. Cosmological observations also open speculative pathways to evidence of a simulated universe. The cosmic microwave background radiation, the faint afterglow of the Big Bang, contains minute irregularities that might be interpreted as artifacts or pixels of a finely tuned simulation grid. These tiny fluctuations could be manifestations of the finite resolution of a simulated reality, akin to how digital images display detail at a certain pixel density. If space-time itself possesses a smallest possible unit, sometimes called the Planck length, this could be analogous to the pixel size of a graphical display. The presence of such minimum thresholds in the fabric of reality makes the case for an underlying digital or computational structure more plausible, even if only as a mathematical analogy. Layered within this speculative framework is the idea that the universe's apparent fine-tuning and constants might be evidence of deliberate calibration. Just as a simulation might require initial parameters set by the creator, the physical constants, like the strength of gravity or the charge of an electron, appear remarkably fine-tuned for life and complexity. Some suggest this isn't coincidence, but intentional design at a deeper level. Multiverse theories add another dimension, proposing that our universe may be one of countless simulations or realities, each with varying parameters. If evidence like these tiny quantum anomalies, mathematical elegance, or cosmological signatures could be shown to be signs of computational processes, it would paint a compelling picture. The universe as an elaborate simulation crafted with purpose, perhaps by an intelligence beyond our comprehension. Implications for human identity and purpose. The prospect that we could simulate an entire universe pushes the boundaries of both philosophical inquiry and computational possibility, bearing profound implications for how we understand human identity and purpose. If our reality is merely a sophisticated simulation, created perhaps by an advanced civilization or a future iteration of ourselves, then notions of uniqueness and intrinsic meaning become fluid. This challenges deeply held beliefs about individual agency, suggesting that consciousness might not be an original or fundamental phenomenon, but rather an emergent property within a constructed framework. In such a scenario, human identity may hinge more on the perception of continuity and self-awareness than on any ultimate, immutable essence. From a practical standpoint, the idea of simulating a universe invites questions about the nature of intelligence and the meaning of existence in a simulated cosmos. If it's possible for a sufficiently advanced algorithm to replicate the intricate web of physical laws, quantum phenomena, and conscious experience, then what does that say about purpose? One could argue that the purpose of human life might be reduced to an artifice, a pattern within a grander computational matrix designed for entertainment, study, or evolution. Conversely, this view could elevate human experience as a unique form of complexity that is itself meaningful, if only because it appears to be real from the inside. The boundary between reality and simulation blurs, questioning whether purpose is inherently tied to a physical substrate or if it exists as an emergent property of consciousness regardless of origin. Philosophically, the simulation hypothesis introduces a radical redefinition of existence. If the universe is a simulation, then the concept of being rooted in an objective, external reality dissolves. Reality becomes transactional, a series of coded events interpreted through conscious awareness. This raises unsettling questions about authenticity and free will. Are our choices genuinely ours, or are they preordained narratives within a larger program? For human identity, this perspective offers a potential liberation or a profound crisis. On one hand, individuals might find empowerment in knowing their consciousness is part of a design system, free from the random chaos of an uncaused universe. On the other, it might foster existential despair or a sense of futility, questioning whether personal purpose has any ultimate significance when all is prescripted or reconstructed from code. In broader terms, simulating a universe also compels us to consider the moral and ethical dimensions of such power. If we could create worlds complete with conscious beings, what responsibilities would follow? Would the simulated entities have rights? How do we define the boundaries of moral obligation when dealing with artificial consciousness? These questions ripple into ideas about purpose itself. If our universe could be a simulation, or if human life is part of one, then the very concept of a divine or ultimate purpose transforms. It becomes a layered, possibly infinite regress, where human pursuits are nested within larger, potentially simulated realities. The exploration of this possibility doesn't just redefine what it means to be human. It challenges the core of human longing for meaning, coherence, and connection within an ever-expanding, possibly simulated cosmos. Future directions and speculative possibilities. Advancements in computational power continually push the boundaries of what might someday be possible in simulating complex systems, including entire universes. Currently, quantum computing stands as a tantalizing glimpse into future capabilities, promising exponentially increased processing speeds and the potential to handle the staggering amount of information that a universe full of particles would entail. If we imagine a civilization reaching a level where raw computational ability rivals or surpasses the scale required to simulate cosmological processes, the question shifts from if to when. Such developments could open doors to creating virtual realities so detailed and lifelike. The distinction between simulation and actual existence becomes nebulous, provoking profound philosophical debates about consciousness, identity, and the nature of reality itself. Theoretically, one promising direction involves integrating principles from both computation and physics. If we accept the universe as a computational fabric, say, a digital or cellular automaton akin to some interpretations of quantum gravity, then harnessing the laws of physics as computational rules becomes an intriguing possibility. This approach offers a bridge between physical theories and simulation capabilities, allowing scientists to reverse engineer the universe's underlying code. Future projects might range from simulating tiny slices of cosmos to entire multiverse scenarios, testing different physical constants, and even altering them to observe hypothetical outcomes. Such endeavors could deepen understanding of how our universe functions, while also hinting at the rules that a universal simulation would need to encompass. Speculative ideas also point toward metasimulation, creating simulations of simulations. As computational models grow more sophisticated, the idea of nesting virtual worlds inside each other becomes less far-fetched. Philosophers starting to ponder whether our universe itself is just a layer within a grander simulation open astonishing possibilities. If advanced civilizations are capable of crafting nested virtual environments, what does this imply about our own reality? Could it be a baby-step simulation designed to explore origins or test existential hypotheses? From a purely technological standpoint, advancing hardware to support such recursive complexity remains a colossal challenge, yet it fuels imagination and fuels debates on the very nature of existence. There are also considerations linked to physics limits, like the speed of light, entropy, and quantum indeterminacy, and how they shape the feasibility of whole universe simulation. As a civilization approaches or surpasses these boundaries, it might develop novel paradigms of information processing that break conventional constraints, allowing for universe-scale simulation. Concepts from theoretical physics, such as holography or emergent spacetime, suggest that reality may be reconstructible from encoded boundary information, which could radically shift our understanding of what it means to simulate reality. Future directions might include harnessing these abstract principles to build universal simulators that replicate entire cosmological histories or concurrent realities, blending deep philosophy with tangible technological innovation. Ultimately, speculative possibilities about simulating a whole universe stretch current scientific understanding into the realm of the philosophical and imaginative. They force us to reconsider assumptions about consciousness, existence, and what it means to create or replicate reality itself. Each leap forward in quantum computation, physics, or artificial intelligence not only brings us closer to these grand endeavors, but also deepens the conversation on the nature of simulation theory, tying together strands of thought from computationalism to ontology, and inviting us to view the universe as perhaps just one of many layers in an infinite hierarchy of realities. The question of whether we could ever simulate an entire universe hinges on the intersection of advanced computation, physics, and philosophical implications about reality itself. Today's supercomputers, despite their ever-growing power, are nowhere near capable of mimicking the vast complexity of the universe. Yet the theoretical possibility invites tantalizing speculation. To undertake such a simulation, one must consider the fundamental limits imposed by the laws of physics. particularly the Beaconstein bound, which estimates the maximum amount of information that can be contained within a finite region of space. As of now, simulating a universe would require processing power that exceeds any current or foreseeable technology by unfathomable orders of magnitude. Still, proponents of the simulation hypothesis suggest that if technological progress continues exponentially, following a trend similar to Moore's law, what is impossible today could become feasible in a far future. On a deeper philosophical level, if such a simulation were possible, it would imply that our perception of reality could be nothing more than computational data processed within some higher dimensional host universe. This echoes ideas from digital physics, proposing that the universe itself might be fundamentally discrete, composed of information akin to the bits in a computer. Actualizing the simulation of an entire universe would involve reproducing every quantum state, particle interaction, and cosmic evolution with near-perfect fidelity. That entails not just tremendous raw processing power, but also an astonishingly detailed understanding of physics, something we are still piecing together at the quantum and cosmological scales. Given the sheer scope, it's worth pondering whether a simulation of this magnitude would then be a simulation within a simulation, creating recursive layers that defy the limits of both perception and comprehension. The notion of simulating a universe also raises questions about the purpose and ethics of such endeavors. Would an advanced civilization choose to create a universe full of conscious beings, knowing they might suffer or experience joy? If we imagine hypothetical future beings capable of constructing such a universe, the moral implications become profound. Are there boundaries, ethical, philosophical, or practical, that prevent never-ending simulations? It's possible that simulating a universe of sentient beings would reveal insights into the nature of consciousness itself, blurring the lines between physical processes and experiential phenomena. The challenge then becomes not just technological, but conceptual, understanding what it truly means to replicate reality on every scale, and whether the act of simulation ever truly creates a universe or just mimics one to the point of indistinguishability. As we wrap up this exploration, it's clear that the idea of simulating an entire universe teeters on the edge of philosophy and technology, raising profound questions about consciousness, reality, and the nature of existence itself. If our universe is a complex program, then perhaps the distinctions between real and artificial blur into something far more intriguing, something that challenges our fundamental understanding of being. The computational limits, ethical considerations, and even the very definition of what it means to exist becomes central in this dialogue, inviting us to reflect on whether a perfect simulation is conceivable or if some aspects of reality are inherently uncomputable. For many of us, this isn't just a theoretical exercise. It's a mirror to our own aspirations, perhaps even a reflection of our potential future. Could we someday become creators within our own multiverses, or are we forever confined to observing the universe's grand tapestry from the outside? This question invites a more personal connection to the universe's mysteries, reminding us that curiosity is at the heart of human existence. If this has sparked your imagination, stay tuned, because future videos will delve even deeper into the intersections of technology, consciousness, and the universe itself. Together, we'll continue questioning the boundaries of reality, pushing the limits of what we believe is possible. And who knows, maybe one day, we'll be the ones writing the code that creates worlds of our own. Keep the wonder alive, and first we'll see you in the next journey into the infinite.